Okay, before we can do a change of variables, we must find the transformation, or if we're given the transformation, we need to find the region that's being transformed. So T is the transformation that'll take some region S, which is in the UV plane, to a region in the XY plane. Now, most of the time, we're going to start with an integral over a region in the XY plane. We will need to find the region S that this transformation transformed into R. So we've got to find our region S. Then we need to be able to convert the function from the variables xy to the variables u and v. And then we put the Jacobian in by evaluating the 2 by 2 determinant. And then we'll integrate over the region S. So let's see how we'll handle this. Okay, let's say that we want to evaluate this integral. Notice this is over the region R. R is defined to be the parallelogram in the xy plane given by these vertices. So we have 0, 0, 0, 1, 2, 4, and 2, 5. Okay, so that's our region R. Okay, now the transformation that we're given here is taking the region S into the region R. But we need to find the region S. So we need to find the UVs. So we're given that X is 2U. Well, that means then that U would be X over 2. Okay, we need to find the V. V would be Y minus 4U, but that would be Y minus 2X, just replacing the U with X over 2. So we can get U and V from XY. So now, to find the region S, I'm going to take the points 0, 0, 0, 1, 2, 4, and 2, 5, and find the corresponding UVs. Now, we could take the whole segments, each of those sides of that parallelogram, and look at how they're transformed. But it's easier if you just take the endpoints, the vertices where those line segments meet, transform those under the transformation, and then just connect the dots. So linear transformations stay, lines stay as lines under these transformations. So to find UV, I know U will be the X over 2. So the X here is 0, so the U will be 0 also. To find V, V is the Y, which is 0 minus 2 times the X. So it'll also be 0. U, which is X over 2, is 0 over 2, which is 0. The V will be Y, which is 1, minus 2 times the 0. So it'll be 1. Now, 2 for the X, the U will be the X over 2, so it's 2 over 2 is 1. Let me go ahead and do the other 2 over here. The U down here will also be 1. And now the Y is, the V is Y, which is 4 minus 2 times 2, so the Y will be 0 there. The V will be 0. And then 5 minus 2 times 2 will be 1. So now this region is transformed into 0, 0, 0, 1, 1, 1, and 1, 0. So this is our region S. So T is mapping this square into that parallelogram. Okay, so now let's transform this integral into an integral using the u's and the v's. Before we do that, though, we have to have the Jacobian. So let's find the Jacobian. The Jacobian of uv. Now we need partial derivatives. The partial of x with respect to u will be 2. The partial of x with respect to v will be 0. The partial of y with respect to u will be 4. And the partial of y with respect to v will be 1. So evaluating this determinant, we get that the Jacobian will be just 2. Okay, so now changing this integral. Okay, we had it over the region R, and this is our function. That's our f of x. This will be this integral over the region S. Now I'm changing all the x's to UV's, to U's. So I'll have 2 times 2U times the y, which is 4U plus V, minus 2 times x. Oops, I forgot to put the Jacobian in there. Times the absolute value, which is still just 2. Okay, so now simplifying, that becomes 4U times V. And then we have that extra 2 out here. I'm just going to go ahead and bring that out in front. And we're integrating over the region S. Now, the region S, well, we just need to describe this square. Well, so that will be 2 times the integral. The U's vary from 0 to 1. The V's vary from 0 to 1. And let's see, the square root of the 4 is a 2, so I'm going to take that out of the square root. And then I'm going to have u to the 1/2, v to the 1/2, just to make it simpler to integrate. Oops, not dx dy, it's du dv. And the order doesn't matter, it's just whatever your limits match up with. Okay, so integrating, and we'll bring that 2 out in front, so we'll have 4 times. Integrating with respect to u first, I'm going to have u to the 3/2 times 2/3. And then our v is still to the 1/2. And that's 0 to 1 for the u values. So we'll have 1 for that u, so we'll have a v to the 1/2. So we've got 8/3. Integrating, we have v to the 3/2 times 2/3. And we just get 16/9. Now in this next graph, you can see what we just did when we changed that integral. Here we were integrating this function over the region R, which was that region down in the xy plane. We transformed it. You can see that little parallelogram in the xy plane here. We transformed it to a different region in the UV plane, just 0, 1 to 0, 1, and came up with this new function. And the region, those volumes under those curves over those regions are the same. So that's why this integral will be the same as this integral. Okay, now sometimes we won't be given the transformation, and we will determine the transformation based on some of the terms in the integrand, or based on the regions. So let's look at this next example. We want to evaluate this integral, and R. Now the region R, 1, -1, 2, 0, is this diamond shape. So if you were to integrate over that region, you know, coming up with your limits of integration would require that you split it into two parts because you would have different bounds starting at x equal 1. So let's see if we can get a different region of integration that wouldn't require us to split it into two different integrals. So looking at the integrand here, we might take some of the variable combinations. The x minus y on the top, let's let that be the u. And then let's just let v be the x plus y. Just to keep it, if you add the 1 in there, it makes the working with it much more difficult. So just keep it with the variable combinations if possible. Okay, so now that's the transformation. Let's see how the points in R are mapped to the region S. Okay, so taking each of these points, 0, 0, okay, so those are our points x, y, and we want to find the UV for the region S. Using this transformation, the U will be the x minus the y, so 0 minus 0. The V will be x plus y, so again, it's just 0. The U, x minus y, so 1 minus -1. Let me just do all the u's first. 2 minus 0, and 1 minus 1. So that's all the x's. And now the v's are all the u's. The v's will be the x plus the y. So take these two added together. And then 2 plus 0, and then 1 plus 1. Okay, so that new region defined by this transformation t will be 0, 0, 2, 0, 2, 2, and 0, 2. A much easier region to integrate over because we can easily get that our two variables both go from 0 to 2. So this is our region S. Okay, so now the tricky part here is that you've got to get your Jacobian, and your Jacobian has to be partials of x with respect to the UV and partials of y with respect to the UV. So here you have to change this transformation to solve it for the x. The t needs to be given as x equal a function of u and v and y equal a function of u and v. So to solve for x and y here, just solve for them as if they're the variables of in u and v are constants. So I can see that if I add the two equations now using the process of elimination, the y's would go away. So I would have u plus v equal to 2x. So I know my x is u plus v, both of those over 2. Okay, so now let's do the same thing and eliminate the x. Let's multiply the top equation through by -1 and then add the two equations. So I'm going to have, adding them together, I would have v minus u equal to 2y. So that means the y would be v over 2 minus u over 2. Okay, so that's the transformation that we're going to use to get the Jacobian. So we want the partial of the x with respect to u, partial of the x with respect to v, y with respect to u, y with respect to v. Partial of x with respect to u would be 1/2. X with respect to v is 1/2. Y with respect to u is -1/2. And y with respect to v is 1/2. So that Jacobian comes out to be a fourth minus a fourth, a negative a fourth, which is just 1/2. Okay, so now setting up the integral, we're changing this integral over to the region S. the integral becomes u over v plus 1 times the Jacobian, okay? And now let's simplify a little bit more to evaluate. We'll pull the 1/2 out. The region S, both variables go from 0 to 2. So just grab your limits of integration using the region S. And I'm going to change this to u to the 1/2 over v plus 1 to the 1/2, just to simplify for integrating. Doesn't matter which order we go in first. Let's do du dv. So 1 over v plus 1 to the 1/2 is a constant. And then we'll have u to the 3/2 times 2/3. And then we're evaluating that from 0 to 2. Now I'm putting these values 0 and 2 in for the u's. So when I put the 2 in, I'm going to have 2 to the 3/2 over v plus 1 to the 1/2, or I could put it up in the numerator, and then we'll have minus 0. Okay, so now let me pull that 2 to the 3/2 out. 2 to the 3/2 is 2 to the 1 times 2 to the 1/2. So that's just 2 times the square root of 2. And I'm going to write this as v plus 1 to the negative 1/2 so I can integrate more easily. Okay, so now if I did a u substitution, I'd let u be the inside v plus 1, but the du and dv are the same, so I'm just going to raise the power by 1. So v plus 1 to the 1/2 divided by 1/2, so that'd be times a 2. And then evaluate from 0 to 2. So we've got 4 times the square root of 2 over 3. Put the 2 in, so I'm going to have 3 to the 1/2. And then minus 4 times the square root of 2 over 3 times just 1. So that would be 4 times the square root of 2 over 3 times the square root of 3 minus 1. Okay, and that's just changing the variables so that we could change this region of integration to make it a simpler integral. Okay, so now let's say that R is a region in the first quadrant bounded by these parabolas. Okay, so x equal to y squared, x equal to y squared minus 4, okay, x equals 16 minus y squared, and x equal 9 minus y squared. Okay, so that region would be in here. Okay, so that's our region R. Okay, so now to evaluate, we just want to integrate the function y squared over that region. We want to change that region so it's a little easier to describe. That would be difficult to describe using our limits of integration. So what I'm going to do is to look at variable combinations here. This first equation, I can think of this as x equal to y squared or x minus y squared equal to 0. And notice this one has the same variables, x minus y squared equal to negative 4. The second one would have x plus y squared equal to 9, and the last one x plus y squared equal to 16. So if I let my transformation, I'm going to let u be x minus y squared and my v to be x plus y squared. My limits of integration will be just obvious then. My u then will go from 0 to -4, and my v would go from 9 to 16. Okay, so we'll again have a rectangular region. Okay, so this is our new region. Yes. Okay, so now the next thing we need to do is we need to solve for x and y here so that we can find the Jacobian. So solving for x will be easy because just add the two equations and you get u plus v equal to 2x. So x will be u over 2 plus v over 2. Do the same type thing. Let's go ahead and just multiply the top one through by -1 and then just add again. So adding, we get v minus u equal to 2y squared. So that would be, put those over 2, and then that's y squared. So that means that y would be the square root of v over 2 minus u over 2. Okay, so now we need to find the Jacobian. The partial of x with respect to u is 1/2. Y with respect to v, or x with respect to v is 1/2. Now the partials of y with respect to u and v will be a little more difficult. Let's write this as the square root of v minus u Okay, let me just rewrite those with the 1/2 power. So this, I'm just going to write this as v minus u over 2 to the 1/2. So the partial of y with respect to u will be 1/2 v minus u over 2 to the -1/2 times the derivative of the inside with respect to u, which will be -1/2. So that's -1/4, and then let's see, that's a -1/2 power, so that's going to be 2 over v minus u to the +1/2, so that'd be over the square root. Okay, so let's see, we can simplify that several ways. I'm just going to leave it that way for now. Okay, the partial of y with respect to v be very similar. But with the positive value there. So that's 1/4. And again, it's going to be 2 over v minus u to the 1/2. Now, if I want to split that up, that would be square root of 2 on top over the 4. And then I've got the v minus u to the square root of that on the bottom. And so the same thing up here. I've got minus the square root of 2 over 4, and then the square root of v minus u. Not sure that's any simpler. Square root of 2 over 4 would be 1 over 2 times the square root of 2. So let me be consistent here. I'm writing those. So when you evaluate the determinant, you get half of this thing minus half of it again. So it's just going to be that thing. 1 over 2 times the square root of 2 times the square root of v minus u. Okay, so now let's evaluate the integral, or change the integral. We're integrating. We're changing this right here over to be the double integral over the region S, which S is defined from -4 to 0 and from 9 to 16. Y squared is just, where'd it go? Y squared is just v minus u over 2. And then we're integrating there with respect to u and with respect to v. The Jacobian is 1 over 2 times the square root of 2 times the square root of v minus u. So that looks like it's going to simplify nicely. I can pull these numbers out. That'll be 4 times the square root of 2 out in front. And now I've got a v minus u on top and a v minus u to the 1/2 on bottom. So this is going to be a v minus u to the 1/2. Okay, I'm just finishing this up. The integral of v minus u to the 1/2 with respect to u. The du, if we made a u substitution, we need a -1. So it's going to be a negative v minus u to the 3/2 times 2/3. Just raise the power by 1, divide by the new power, but be sure you take the derivative of the inside to adjust for that, change of variables. dv, we're evaluating that from -4 to 0. Okay, putting 0 in for the u, we would have v to the 3/2 and then minus -4. And we would have v plus 4 to the 3/2. Okay, so cleaning this up out in front, we'd have -1 over 6 times the square root of 2. And now integrating with respect to v, we would have 2/5 times v to the 5/2 minus 2/5 times v plus 4 to the 5/2. And we're going from 9 to 16 here. So I'm going to go ahead and pull that 2/5 out of everything. So we're going to have 16 to the 5/2 minus 20 to the 5/2 and then minus, now this thing is multiplied by everything, 9 to the 5/2 minus 13 to the 5/2. Now you can simplify this. 16 to the 5/2 is just the square root of 16, which is 4 to the 5th, it's just 1024. 9 to the 5/2, the square root of 9, which is 3 to the 5th, is 243. 20 to the 5/2, you could pull a 2, take 4 to the 5/2 times the 5 to the 5/2. You can do a lot of simplification, but ultimately you're going to approximate this, it's 18.79.